Welcome to this professional training module. We will explore the critical relationship between power quality and energy storage systems. Our roadmap is divided into four modules. First, fundamentals, examining waveform integrity and the total harmonic distortion formula. Second, mitigation, learning to deploy passive and active filters alongside statcoms to correct voltage flicker. Third, storage, comparing technologies and highlighting the 90 to 95% efficiency of lithium ion BESS. Finally, standards, reviewing global compliance requirements like IEEE 519 and IEC 61000 for grid stability. At the heart of modern power management is waveform integrity. In an ideal grid, voltage and current flow as pure, perfect sinusoidal waves. This perfect sine wave ensures efficient energy transmission. However, real world systems face nonlinear loads, which introduce significant noise and distortion into the grid. When the waveform deviates from this ideal shape, it creates hazardous harmonic frequencies that severely stress the electrical infrastructure. These distortions directly cause equipment heating, premature aging, and malfunctions, making waveform integrity the absolute foundation of power quality. To quantify the distortion we just saw, engineers rely on a critical metric, total harmonic distortion, or THD. It is the mathematical foundation of power quality analysis. The formula for voltage THD is expressed as the square root of the sum of the squares of all harmonic voltages, divided by the fundamental voltage. In this equation, V1 represents the fundamental frequency, typically 50 or 60 Hz, which is the pure intended power. Vn represents the unwanted harmonic components, such as the third, fifth, or seventh harmonics generated by nonlinear loads. This ratio reveals the percentage of pollution in your system. High THD directly translates to severe physical consequences, including extreme energy losses and catastrophic transformer saturation. To meet strict power quality standards and eliminate harmonic distortion, engineers often turn to a foundational solution, passive LC filters. These filters consist of an inductor and a capacitor connected in series. They are precisely tuned to a specific harmonic frequency, such as the fifth or seventh harmonic. At this tuned frequency, the LC circuit creates a low impedance path. Instead of flowing into the grid, the damaging harmonic currents are safely shunted to ground. While passive filters are highly cost effective and robust, they have limitations. They offer only fixed tuning and carry a risk of parallel resonance with the system impedance. While passive filters offer a baseline defense, modern environments with dynamic loads demand a more intelligent solution: active power filters. Unlike passive systems with fixed circuits, an APF acts as a real time corrector, continuously monitoring the line current for deviations. When harmonic distortion is detected, the APF's power electronics immediately generate a precise compensating current. The principle relies on phase cancellation. The injected current is exactly 180 degrees out of phase with the harmonic noise. This active injection cancels the distortion instantly, restoring the system to a pure sinusoidal waveform. Crucially, APFs adapt to fluctuating loads in real time and simultaneously correct power factor, ensuring optimal grid stability. While active filters offer precision, high-power industrial motor drives often rely on a more robust foundational solution, the 12-pulse rectifier. This system utilizes a phase-shifting transformer equipped with two secondary windings, typically one delta and one Y configuration. This design creates a precise 30-degree phase shift between the two bridges, naturally canceling out the problematic fifth and seventh order harmonics. For ultimate power quality, facilities deploy hybrid filters. These combine the cost effective bulk mitigation of passive LC circuits with the dynamic correction of active power filters. We now address another critical power quality issue: voltage flicker. Flicker is the rapid fluctuation of voltage that causes visible changes in lighting intensity, directly impacting human perception and productivity. In industrial environments, this is frequently caused by large, fluctuating loads. A primary culprit is the electric arc furnace, which draws massive erratic currents, destabilizing the local grid. To quantify this, engineers use the POST index or short term flicker severity. Measured over a standard 10-minute window, it evaluates voltage variations against human eye sensitivity. The critical compliance threshold is a PEAST value of 1.0. Exceeding 1.0 makes the flicker highly perceptible and irritating, signaling an urgent need for mitigation. To mitigate voltage flicker caused by industrial loads like arc furnaces, we use dynamic reactive power compensation at the point of common coupling or PCC. The two primary technologies used for this are static var compensators, known as FCCs, and static synchronous compensators or STATCOMs. While both inject or absorb reactive power to stabilize voltage, STATCOMs offer significant advantages over traditional SVCs. STATCOMs provide a much faster response time, typically under a cycle, and require a significantly smaller installation footprint. Crucially, STATCOMs maintain full reactive current output even during severe low voltage grid faults, ensuring stability when the grid needs it most. As we transition from mitigating waveform distortions, we enter the second critical pillar of modern power management: energy storage systems. Historically, power generation had to perfectly match consumption at every single millisecond. Any imbalance immediately caused power quality issues, such as severe voltage sags or frequency deviations. Energy storage fundamentally changes this dynamic by decoupling generation from demand. By acting as a massive buffer, an ESS can rapidly absorb excess energy or inject power within milliseconds. This rapid response is essential for key grid applications, peak shaving, emergency backup, and instantaneous frequency regulation, where modern BESS units operate at 90 to 95% round trip efficiency. Let's explore how these diverse storage technologies stabilize our increasingly renewable heavy grids. To effectively manage modern power grids, we evaluate energy storage technologies based on three key metrics: power density, energy density, and discharge time. Let's map out the landscape. Pumped hydro provides massive bulk energy storage with long discharge times. It excels in total capacity, but has lower power density and strict geographical limits. Conversely, flywheels deliver extremely high power density. They provide rapid, sub-second responses ideal for short-term power quality correction, but they store very little total energy. Vanadium flow batteries offer a unique advantage. Their power and energy capacities are completely decoupled, making them highly scalable for medium to long duration storage. Finally, lithium ion BESS occupies the crucial sweet spot. With high power and energy density, plus modular scalability, Li-ion has become the dominant choice for modern grid applications. Matching the right technology to the specific grid requirement is the foundation of modern power management. When evaluating energy storage for modern grids, one metric stands out: round trip efficiency. Battery energy storage systems, or BESS, achieve an exceptional 90 to 95% round trip efficiency. This measures the energy retrieved from the battery compared to the energy injected during charging. The minimal 5 to 10% loss primarily occurs during DC to AC conversion in the power inverters and through the thermal management systems. This high efficiency sharply contrasts with alternative technologies. Flow batteries typically operate at 70 to 75% efficiency, while hydrogen storage yields less than 40%. By minimizing these conversion losses, BESS provides the highly responsive energy dispatch required for critical applications like frequency regulation. In modern grids, maintaining a stable frequency of 50 or 60 Hz is a constant challenge. When generation and demand mismatch, grid frequency fluctuates. Traditional thermal power plants were historically used to balance this, but their mechanical systems are simply too slow to handle the sudden shifts of renewable energy. This is where battery energy storage systems, or BESS, become essential. BESS provides what is known as primary frequency response, driven by advanced controllers, A BESS unit detects frequency deviations and responds in mere milliseconds. It dynamically injects power when frequency drops and absorbs excess power when it spikes. Operating at 90 to 95% round trip efficiency, BESS instantly stabilizes the grid, acting as a high speed digital shock absorber. To ensure the stability and reliability of modern interconnected power systems, strict adherence to global power quality standards is absolutely mandatory for all operators. In North America, IEEE 519 serves as the definitive benchmark. It establishes strict limits on voltage and current harmonic distortion at the point of common coupling. Internationally, the IEC 61000 series provides a comprehensive framework for electromagnetic compatibility, or EMC. It ensures that diverse equipment can operate seamlessly without introducing intolerable grid disturbances. Beyond these broad international frameworks, localized grid codes dictate utility specific compliance requirements. These codes dynamically address local grid vulnerabilities and are often significantly more stringent. Failing to meet these rigorous criteria can result in severe financial penalties or even forced grid disconnection. We've covered a lot of ground today. We started by defining waveform integrity, examining the total harmonic distortion formula, and exploring mitigation techniques like active and passive filters. But as we've seen, modern power management is no longer just about filtering out noise. It requires dynamic, integrated solutions to handle rapid fluctuations. This is where energy storage systems, particularly high efficiency BESS, bridge the gap. By combining harmonic mitigation with millisecond level frequency regulation, we create a truly resilient ecosystem. For engineers and operators, the ultimate takeaway is clear. Achieving compliance with IEEE 519 and IEC 61000 demands a holistic approach, uniting power quality and energy storage for unparalleled grid stability. Before we conclude this training module, let's reinforce your learning with a quick technical knowledge check. Recall the total harmonic distortion formula, THD underscore V, equals the square root of the sum of Vn squared divided by V1 times 100%. In this critical equation for power quality, what exactly does the denominator V1 represent? Is it A, the total RMS voltage, B, the fundamental frequency voltage, or C, the peak harmonic voltage? The correct answer is B. V1 represents the fundamental frequency voltage, which serves as the essential baseline to measure the relative magnitude of all harmonic distortions.